It's Paul again, this time with a script designed to show you how you can use R to find and classify all the critical points of a rather messy function. We'll need to be able to take numerical derivatives, so we load the appropriate library, and we load up the function. I found this as an exercise in the Hubbard textbook, and it suggests that you better use a computer on this, because if you try solving the equations that you get by setting partial derivatives to 0, you won't be able to do the algebra. So here's our function of x and y, minus x cubed plus y cubed plus xy plus 4x minus 5y. We need this version in order to plot the contour lines. Somewhat annoyingly, if we want to calculate numerical derivatives, gradients, Jacobians, and the like, we need the same function expressed in terms of a single vector. So I replace x by v1 and y by v2 and write a second version. The way to start our exploration is by plotting contour lines. So let's choose sequences of values for x and y that go from minus 5 to 5. Use the outer function to make a matrix of function values and plot the contour lines. We don't have many contour lines, but there's one giveaway. Whenever you see a closed contour line, you start looking for an extremum inside that contour line. Since the contour line is centered roughly near minus 1, 1, we bracket that point, running x from minus 2 to 1, running y from minus a half to 2.5, and plot a slightly more close-up version. And now you see the contour line for minus 8 is a closed curve, but you don't see anything inside it. So, somewhere inside there, we appear to have found a minimum. You can see the contour lines are going down, down, down as we approach that point. Again, set up a sequence of x values and a sequence of y values that bracket the point minus 1.3 to 1.5. Plot the contour lines. Now we've got it. It's somewhere inside that circle. And if we ask the contour function to plot levels between minus 9 and minus 9.1, we've got an excellent approximation. Now here's the classic method for finding critical points. You use standard techniques of single variable calculus to get the partial derivatives. So the first partial derivative here is going to be minus 3x squared plus y plus 4. The second partial derivative, looking at the original equation again, is going to be 3y squared plus x minus 5. And we expect those both to be 0 at the critical point. We don't have the critical point, but we've got a pretty good approximation to it now. It's roughly at x equals minus 1.35, y equals 1.45, and when we evaluate the partial derivatives there, we get something that is pretty close to 0. Interestingly, while we used our knowledge of how to differentiate polynomial functions, we didn't need it. If we just ask for a numerical computation, we get exactly the same values. So we're close. How do we get closer? Answer, we use Newton's method. In order to use Newton's method, what we have to do is calculate the Jacobian matrix from these partial derivatives. Call that A. But numDeriv actually has a function that will do that automatically for us. It's called the Hessian function, produces exactly the same matrix of second derivatives. And now we use the standard Newton's method update formula. And what have we found? V1, the value of our minimum, is at minus 1.34, 1.45, and the value of the function there is around 10 to the minus sixths. Sorry, I take that back. The value of the function there is minus 9.09. that is a very good approximation to the minimum value of the function. As if it weren't obvious, we could check that this is a minimum by using the Hessian matrix. First, with the vector version of our function, we calculate the gradient. We get close to 0. That confirms we've got a critical point. Next, we calculate the Hessian matrix H of partial derivatives. And when we look at that, we discover that it's got a positive determinant. That means we've got an extremum. And the fact that the values along the diagonal are both positive means that things are going to go up. We have found a minimum, but the usual way of doing this in the 2 by 2 case is add them together. If the determinant's positive and the trace is positive, you've got a minimum. Okay, 1 down, 3 to go. Let's go back and look for another extremum. We'll have a second look at our original plot now that we know what to do. And we look at where those two contour lines for 0 seem to push apart, somewhere near x equals 1, y equals minus 1. There may be another extremum. So we bracket that pair of values and plot the contour lines, and we've got it. Somewhere inside that contour line for 6 is a critical point, which is a maximum of the function. Make a guess about where it might be. Check the partial derivatives. They're close to 0, but not good enough for us. However, Newton's method usually works wonders, and when we use the standard Newton's method, this would be a real pain with pencil and paper, by the way, we find a place where the partial derivatives are both very close to 0. Namely, one of them's minus 0.002, the other is plus 0.004. And when we evaluate the function there, we find 6.08, the maximum value of the function. We can reinforce our conclusion by drawing the contour lines near the maximum. We just plot the function very close to the maximum, and you see the typical behavior at a maximum. There are contour lines that encircle the maximum, and the values on the contour lines go up, up, up as we approach the maximum. We can automate this. Check the gradient. It's 0. That confirms that we've got a critical point. Calculate the Hessian at the same location. It has a positive determinant. That means we have an extremum. The entries on the main diagonal are both negative. That means things are going up as we move away from the critical point, and therefore, things are going down as we move away from the critical point, and we have a maximum. Originally, when I explored this function, I missed the last two critical points, but now I know how to look. Look at that 0 contour line. There's a place where it comes perilously close to crossing itself, and the reason it doesn't is that we didn't choose the right value for the contour. But there's probably some value near 0 for which the contour line would pass in two different directions through that point. Our suspicion focuses on a place where x and y are both close to 1.3. So let's zoom in for a closer look. And those hyperbolas are pretty much a giveaway for a saddle point. Circles or ellipses tell you you've almost certainly found a maximum or minimum. Hyperbolas like this tell you you've almost certainly found a saddle point. And we know the values near that point because we can see the contour lines for 0.2 and 0.3. So let's ask for contour lines in between. And now if you look at that blankish region in the middle of the plot, you see as you move up and down, the values go up. As you move right and left, the values go down. That's typical of a saddle point. It's a critical point, but it's not an extremum. There are larger values and smaller values nearby. Off that graph, we can read the approximate location of the saddle point, and so we zoom in for a closer look. There's typical behavior near the saddle point, and we can actually plot some contour lines that come closer to it. Okay, here's our saddle point. X equals 1.31, y equals 1.11. Have we got it right? Well, we calculate the two partial derivatives. They're pretty close to 0. But since we have a really quick way of doing one iteration of Newton's method, we can improve on that and get a place where the partial derivatives are very, very close to 0. We evaluate the function at that point. The value at the saddle point is 0.263. That's probably of no particular interest to anyone. The value at a maximum or a minimum may be significant in an application. At a saddle point, it's probably not. The important thing is to notice that near that point, there are larger function values and smaller function values. This is a critical point, but it's not an extremum, and we can confirm everything by taking numerical derivatives. First, we just check that the partial derivatives are 0. Then we compute the Hessian matrix, and in this case, the determinant is negative. If you get a negative determinant, you know you've got a saddle point. When I looked at the original equations for the partial derivatives, they were quadratic in one of the variables, and I realized I could actually eliminate either x or y and get a fourth degree equation for the other. So if we had a fourth degree equation for x, we've already found 3 values of x that lead to critical points. There's probably a fourth critical point. And now that we're becoming skillful, we look at the original contour lines and we know what to look for. If you go up along the line where x equals -1, you can see that that contour line for 0 gets close to itself. So we focus our suspicions on the region where those green lines are crossing and zoom in on that point. Okay, there are the hyperbolas. We have found another saddle point. We can plot contour lines for more function values and figure that the value of the function is going to be somewhere between 2.6 and 2.7, and we can read off the graph the approximate location of the saddle point. Newton's method has been working well for us, so let's just use x equals -1, y equals -1.5. We calculate the partial derivatives there. They're not particularly close to 0, but they're not too far away, so Newton's method will probably serve us well. Do one iteration of Newton's method to get v1, and now we've got the partial derivatives equal to 0 within 1/100th. That's good enough for me at the moment. I'll evaluate the function at the saddle point, which is not of any particular importance, and finish off by having a look at the Hessian matrix. First, let's just make sure that the partial derivatives are both 0 at our critical point, then compute the Hessian, and if you look at its determinant, you discover the determinant is negative. That rules out a maximum or minimum. It confirms a saddle point. In my opinion, this example is much more instructive than the ones that you can work with pencil and paper, where you spend most of your effort trying to solve nonlinear equations that have been rigged to have integer roots. Here we're really looking at the behavior of the function, and I would say if you understand this example in all detail, you have a much better understanding of critical points than I ever did when I was studying this subject in the pre-computer era.